Good afternoon, everyone. Welcome to today's two-phase flow system class. Today's lecture two. Um, Today, I want to introduce you the concept of drag force. So first, I'm giving you the definition of drag force, and then the correlation, which means how we quantify or calculate the drag force, and then give you some examples in our lives for you to better understand what is the drag force. So last time we discussed the state of art approach to study to simulate two-phase flow, which is the two fluid model. Well, in the two fluid model, we consider the mass, momentum, and energy equation with respect to each phase separately. So we can see that in this momentum equation, there is a drag force here need to be determined to solve this equation. The drag force is actually very common in our lives. Just imagine when you run in a heavy wind or when you swim in a water pool, you can feel the force that resists you to move. Um, so before I start, let me give you the definition of the drag force. The drag force is the force in the direction of the upstream velocity. So if you like stand in the wind is blowing to you. So the force you feel is the same direction of this direction. So how we calculate this drag force in engineering systems? Here gives you a correlation Fd equals to negative CD over 2 0 V square and area. And about this equation, so this CD is a drag coefficient, so it's a function of the velocity, viscosity, surface smoothness, and the shape. The viscosity, I mean the fluid viscosity. Like if you run in the air, the viscosity means the viscosity of the air. So if you swim in the water, it's the viscosity of the water.
So
Yep.
I have a question. Okay, so the viscosity describe what property of the water or air?
So you can imagine the movement of the water and oil. If you pull a water out of the cup, the water directly fluid out of the cup. However, if you draw a cup of oil, it's hard to move, right?
Oh,
It's because it has larger viscosity than water.
okay.
It's not easy to flow.
Yeah, I see.
Yep.
I have another question that is this kind of drag coefficient a property of a kind of fluid itself or decided by some other, like the density or some other things?
Okay, so the viscosity means the viscosity of the fluid. So the surface smoothness is objective, like yourself in the air is the smoothness of yourself. Or if a car moving in the air, it's the smoothness of the car. And the shape is also the objective.
Okay, yeah, I see. It
Yeah,
is
so
decided by the three.
Yeah, it's
Okay.
actually a combination of the fluid and the objective. Yeah. So rho is the density of the fluid. The v is the relative velocity. Is so here the negative sign here means the direction of drag force is opposite to this velocity direction. So if the fluid is flowing this way, the drag force is this way.
Okay.
So it's a resistant force. And A is a projected area normal to the velocity. So if the velocity direction is this way, the projected area is this. It's normal to this direction.
Okay.
So for your to better understand this correlation, I'll give you some examples in our lives. First, imagine if you run a heavy wind like this, or you just walk in the weather without wind.
Mm-hmm.
Which kind of situation can you feel more resistance?
With wind.
Yeah, of course, with wind. It's because it's the drag force in this correlation is determined by which factor is different.
Mm-hmm.
Which factor? So yeah.
The relative velocity.
Yeah. Good.
But I mean, if you go into the same direction with the wind, then
There's not the drag force, right?
Yeah.
Here means drag force is a resistant force. It's present or obstacle to your movement. It's not help you to move. So another example is like a hawk in the air when he finds some food on the ground, like he found a snake. And usually to tighten his body, collect his wings, to dive, to catch the food. So when it's dive, it accelerates, right?
Yeah.
So which means it reduces the drag force. It's because which of the factor?
I guess it's a projected area, right?
Yeah. So
But I have a problem. I mean, it's hard to see. I mean, when the area decreases, the relative velocity increase, right? And so I can really tell. I cannot really tell how the drag force changes.
Yeah, that's good. Yeah, that's a good question actually. I didn't think about that. But from our tuition, we can see that usually they dive, they must accelerate, right?
Yes.
So the overall effect must be the drag force is decreased.
Okay.
So there's not only this one drag force, there's a gravity.
Yeah.
Will affect its acceleration.
Okay.
So another example is when you walk in the water and when you walk in the air, which one will you feel more resistance?
In the water.
Yeah, it's because
of the drag coefficient.
Yeah, it's because the viscosity of the water is larger than that of the air. And another example is a car. Nowadays, a car is designed more streamlined. Which I mean by that is, you can imagine the car is like in this shape. And in the old days, the car is like a big head, like the front is like this shape.
You mean it is perpendicular?
Yeah. So we designed that the car in this way to reduce the drag forces because we reduce which factor?
Is that the surface smoothness in the drag coefficient?
No, actually it's the shape of the car.
Oh,
so
okay.
Yeah, if you design a streamlined car, its shape is different from that older ones. It will reduce the coefficient by that streamlined car.
Okay, I see. That makes sense.
Yep. And the last example is the surface of the car or a swimsuit is your design smooth, right?
Yes.
Yeah, that's because of the surface smoothness. So, can you think about another example in our daily life, like competitive swimmers. They use to reduce this drag coefficient. Imagine an example like they get a more smooth surface of their body.
Yeah, they wear the swimsuit.
Yes, swimsuit, and also they wear a cap head, right?
Yeah.
And also they sometimes shave their hairs on their hand, on their chest,
Yeah.
on their leg.
Yeah.
That will also help. Maybe it's to our it's not that significant, but they are competitive swimmers. They want the difference is not that big for them. So yeah. Um, so to sum up in today's class, I talked about the drag force. It's a function of the drag coefficient, density, relative velocity, and project area. Then I'll give you some examples to explain what I mean by these factors. So, do you have any questions?
No, thank you.
No, thank you.
Okay. Okay. Thank you.